Introduction matters. So today I'm going to show you how your microservices are at danger of a new class of inconsistencies and how you can gradually fix them without compromising performance nor scalability. So traditionally, web applications begin as monoliths with a single application service that receives user requests and a single data store where application state is stored. However, as application usage grows and development teams expand, these monolithic structures can hinder the provision of a scalable and high-performing application. When faced with these issues, developers turn to microservice-based architectures as a solution. They realized that they could split and decouple functionality between various services, but also split data between different storage systems, each tailored to specific service requirements. The flexible nature of these loosely coupled components and the ability for each service and data store to scale independently attracted the community. However, microservices also have their downsides. To highlight the main problems of adopting microservices, here's a snippet of a blog post by microservice guru Martin Fowler. He discusses challenges like dealing with distributed systems and the increased complexity of management and deployment. However, today we'll focus on one issue, consistency, or the lack of it. He makes this interesting claim that if you adopt microservices, you have to let go of stronger consistency models and accept eventual consistency as your only choice. Another notable example came from Facebook, where in the paper from HotOS 2015, authors state that to provide strong consistency across services, it would result in impacting availability and latency. However, within the same paper, they also report a real example that perhaps some of you, as users of their platform, have experienced firsthand. And so, in this example, we have Bob, who is a Facebook user based in Europe, who is posting a new update for his followers in the US. So Bob's post is first received by a web server, which then contacts the post storage service to create the post object in the corresponding data store, and after, the notifier service is contacted to create a notification for said post in a notification queue. And then the replication of both of these objects is started. Now, assume that in this case, the replication of the notification is faster than the replication of the post. And in this way, the first event that takes place is the delivery of this notification to Alice in the US. After Alice receives this notification, she attempts to retrieve the post from the post storage service. But instead, she gets a post not found error. Looking closely, at this point, the object is still replicating to the US. The post does in fact exist, but it is just experiencing a delay in becoming available in the US due to the replication protocol. In this scenario, we encounter what we call a cross-service inconsistency. These inconsistencies arise from the interplay of different replication and consistency semantics. Notice how in this scenario, the inconsistency was observed even though both the notification and post-storage data stores are each functioning correctly with their respective replication and consistency semantics. Despite all of this, and even if this service offered guarantees such as causal consistency, it is still possible for the final outcome to be incorrect. Now, the previous example showed how cross-service inconsistencies are visible even in very small architecture, so a natural question to ask is, how likely are these events in a more realistic scale? In the real world, complexity is the norm, as depicted by these diagrams showcasing the interdependencies between services at companies like Amazon, Netflix, and Twitter. And in more recent publications, Uber reported that the average number of RPC calls per request exceeds 100, with some reaching into the thousands. And Internet Alibaba, 25% of user requests involve contacting more than 10 unique stateful services. Despite the lack of concrete evidence from these platforms, we argue that in these settings, there are probably more cross-service inconsistencies than developers are even aware of. And so, now that I've motivated that cross-service inconsistencies are a real issue in modern microservice architectures, I'll next explain how we capture these inconsistencies through our new cross-service causal consistency model, an extension of Lamport's causal consistency to the cross-service scenario, And lastly, I will discuss how Antipode prevents these inconsistencies by enforcing XUI using a scalable, gradual, and easily deployable solution. But first, let's discuss the challenge of both capturing and preventing cross-service inconsistencies. So the first challenge is a semantic limitation challenge. So we looked at existing definitions of causal consistency, which are based on Lamport's happened before relationship. And as we will see next, we found out that they do not capture the relationship that are at the root of cross-service inconsistencies. And therefore, we needed to extend existing definitions. The second challenge is related to tracking those dependencies. Application call graphs can be quite complex, as we have seen, so propagating causal dependency alongside these interactions can become a significant burden. The third challenge is dependency enforcement. So a common approach to enforcement involves enforcing causal dependencies at each read operation. However, this can result in end users experiencing delays while they wait for these cross-service dependencies to be visible, which is even worse in the case of geo-replicated scenarios. And finally, developers don't want big bang type of solutions that require changing thousands of services or replacing the data stores they already use. So any solution must allow for gradual adoption. We start by addressing the semantic challenge. To understand why Lamport's happened before relationship is not aligned with today's microservice applications, we go back to our running example of the post-notification application. We can see here that the various different interactions, RPC calls, data store operations, form two simple call graphs. The first call graph begins with the user's request for a post, and then forks to two different sequences of events. The top branch for writing the post data and then replicating towards all the replicas, and the bottom branch, which propagates the notification for that new post and finishes when all notifier instances receives the notification, and in this case in the US. The second call graph starts when the follower actually clicks on the notification in an attempt to read that post. To this grouping of events, which are triggered in response to a single client request, and in this case, the post creation on the left at orange, or the clicking on the notification link to read the post on the right in blue, we call a lineage. The concept of lineage captures precisely what needs to be extended in Lamport's happened before, because it connects groups of events that may be causally related as a whole, which happens in this particular case since there's no notification without creating the corresponding post first. So let's analyze what will happen if we use the standard Lamport's happened before and how lineages address the mismatch within microservice deployments. So in this case, the post-upload action to the left is forking to do different chains of events corresponding to the post and the notification storage, which in the setting that the happens before was originally designed for would correspond to two concurrent set of events that proceed independently. Note here that this is no longer the case in the microservice setting, because both sets of events stem from the same client request, and since they have an intrinsic relationship between them. Coming back to the example, when the notification written by orange is read by the rightmost blue event, this establishes a standard happens before relationship between the lower branch of the orange set and the new event in the blue set. But this relationship is not established with the upper branch, since the two branches were considered independent to begin with. And therefore, at the top, the blue read happens concurrently with the orange write. And then things get a bit more complicated. And this is because Lamport's causal consistency does not enforce any particular ordering between two actions that are deemed as concurrent. And in this case, as I have shown you, without proper ordering, we risk ending up with a cross-service inconsistency. To solve this problem, we propose cross-service causal consistency, which extends the Lamport's definitions to enforce order in these scenarios. We do that simply by resorting to our lineage concept and define that as soon as there's a Lamport happened before between two events from two different lineages, then a lineage happened before relationship is established between two lineages as a whole. And from that point on, any event from the preceding lineage has to be visible to the subsequent one. The intuition here is that as soon as one event from blue reads an output from orange, then from that point forward, any event from orange needs to be visible to blue. We have formal definitions of both XUI and lineages in our paper. Go check them out. So we have there's a more theoretical challenge of determining what is the specification we are trying to meet by introducing XUI. And we'll now go over the 3 more practical challenges on how to enforce this specified behavior through Antipode. Antipode prevents cross-service inconsistencies by tracking causal dependencies and enforcing XUI through an application-level API. It addresses the practical challenge we mentioned before through 3 different techniques. The first challenge is dependency tracking, so how can we capture and propagate these causal dependencies throughout these large applications? And fortunately, this problem was actually solved by the distributed tracing community. Tools like Jaeger, OpenTelemetry, or Zipkin are nowadays commonly deployed within these applications. We take advantage of this infrastructure and piggyback consistency metadata on it, resulting in practically no changes in the deployment. Next, we look at how Antipode enforces these tracked dependencies. And let's jump to the end of our interaction when we want to read the post corresponding to the notification. So in traditional causal consistency approaches, the enforcement of a set of causal dependencies happens implicitly at every read operation, just like when you attempt to read a post. However, this approach forces the end client to actively wait for the replication to finish, which is far from ideal. We believe developers should have the freedom to hide this delay from the users in a way that makes the most sense for their applications. And in this case, the best approach is to shift the enforcement to before the user gets the notification. And in this way, the wait time doesn't really affect the end user that much. Users will just get the notification slightly later. To achieve this, we decouple the enforcement of dependencies from the actual data store read operation and provide an API we call barrier. Barrier is what we consider explicit enforcement, since developers have the power to choose a place where the visibility of a set of dependencies is to be enforced. Finally, we take a look at how we allow for gradual adoption and avoid changes to existing services, especially in data stores. The strategy here is similar to the one used by Peter Baylis in his work with causal consistency. So we use bolt-on shim layers that allow us to upgrade existing data stores with XUI consistency semantics. With this technique, we require no changes to the internals of data stores. All we need is a straightforward modification to the data schema of the underlying data store to piggyback our lineage metadata and replace read and write operations with a corresponding shim version. So overall, we capture causal dependencies leveraging existing tracing frameworks. We provide an application-level API that allows developers to control when to enforce those dependencies, and we use bolt-on shim layers, allowing for a more gradual adoption. Let's look at some evaluation numbers now. So we evaluate the impact of preventing cross-service inconsistencies with Antipode using 3 different applications. First, a micro-benchmark based on our post-notification application, based on AWS Lambda, where we use different combinations of out-of-the-box public backends for both post and notification data stores. Then we also use 2 benchmarks with a size that is closer to real-world applications, namely that star bench and the train ticket benchmark. In this presentation, I'll show results for both post-notification and the dead star bench. We center our results in 2 distinct metrics, latency and throughput, and the consistency window. The consistency window metric tries to answer the question of what is the extra wait time for a consistent result. As we saw, without Antipode, microservice applications might suffer from cross-service inconsistencies. The consistency window shows us how long an inconsistent read should have waited to get a consistent result. The Antipode barrier enforces this wait, thereby ensuring a consistent read. This extra wait time is visible in this plot, and as we discussed in the paper, it's almost exclusively due to each data store replication semantics. For instance, notice the difference between the consistency window in stronger consistency environment like MySQL versus S3. Then we looked at latency and throughput to find out the true overhead of using Antipode. And here we are able to see its low impact, which is as much as 2% on application throughput. So, to conclude, I've shown you how your popular microservice applications might be at risk of cross-service inconsistencies. I've shown you how XUI captures these relationships by extending the Lamport causal consistency to lineages. And last, how Antipode prevents these inconsistencies by enforcing XUI in a scalable solution that is of gradual adoption and easily deployable. Code is available on GitHub. Thank you for your time. I'll gladly take questions now.
Hello, Reginald Frank from UC Berkeley. Really nice talk. One question that I had though was, it seemed like in some of your examples, there were hundreds of different RPC calls for a very small number of user interactions.
Yeah.
Do you think that this is a scalable solution to kind of enforce synchronization points between different services then when you might be touching a lot at once?
Yeah, so regarding the first point of how large these applications have become, so we actually tested with a reasonable size application like that Starbench and such. We are unable to reach like the Facebooks and Twitters and Netflix of this world, but what we end up with was very good results, like that 2% of throughput actually proves that. We would like to test Antipode against this and to deploy Antipode in these larger applications, so we have larger chains of events to test this. But we think like the design and the overall semantic part of XUI tries to reduce the set of dependencies that we actually enforce to like a reasonable amount.
Thank you.
Hi, great talk. Konstantinos Kalas from UPenn. I really like the design of the system, very elegant.
Thank you.
The question that I had is, with respect to the slide where you explained the limitations of causal consistency, I think it was slide 15. The problem, my confusion is that I'm not sure the upper and the lower branch are actually concurrent, because the post storage does happen before the notification. So, but then you said that they're concurrent. So yeah.
Sorry for the interruption. So the notification happens before the post happens before the notification, but the replication of the post does not. Okay, so that replication on top does not. So if, for instance, post storage was a strongly consistency data store, then you could say that both writing the post on the local replica and replicating to all the replicas would be like a true, let's say, happens before between that whole upper branch. But in the case of asynchronous replication, which it is the most common scenarios in these large-scale applications and in microservice deployments in general, that's what happens the most. And in that case, the replication part is not.
Makes sense. Okay, thank you.
Thank you for your question.
Quick third question.
Hello, Hernán Ponce de León, Huawei Dresden Research Center. Did I understand correctly that it's the responsibility of the application developer to place those barriers?
Yeah.
Do you have any way in actually helping the developer figuring out where those barriers should be, like, or if the barriers that they place guarantee correctness of the application, or even how to optimize those?
Thank you for a great question. So actually, you can run Antipode in a kind of like debugging mode, where you actually see the inconsistency happening, and you are not enforcing the barrier and the extra wait period. So that would actually be a way for you to use Antipode to figure out where to place the barriers to, like on this debug mode, to check where those inconsistencies are happening. Besides that, another common thing that we found out, like from our own experience on deploying Antipode in these benchmarks, is looking at the data model of specifics. So, for example, if the notification is mentioning like a key from the post, right? That's a potential cross-service inconsistency that you might have there, because you're accessing referencing data from another data store in another.
Yeah, thank you very much.
No problem.
We actually don't have any time. Let's take the remaining question offline. Let's thank the speaker again.
Thank you.
And, fourth speaker.